Example 11.4. Here we have a mass M1 and a block M2 are connected by a light cord that passes over a pulley. The radius of the pulley has a capital R, and the mass of the rim, I mean only the border of the pulley has a mass M, this one. But the spokes have negligible mass. Okay. Find here we have the block slides on a frictionless horizontal surface. We don't have a friction between M2 and the plane. Find the expression A of M1 and M2 using the concepts of angular momentum L and torque tau. In this problem, I will solve it in details, especially how can we calculate the magnitude of L and tau, how can we calculate the directions of L and tau, and after this we can calculate A. Before, let me explain many points. Here you have a flexible, we have an inextensible cord. The first point, in the case of inflexible cord, in this case we can say V1 equals to V2 equals to V, and A1 equals to A2 equals to A. Okay. The second point, you know, we have a light cord. In this case, you know, here we must have T1 equals to T1 and T2 equals to T2. Here we have T1 and T2. No, T1. And here we have T2 and T2. So here we have T1 and T2. The third point, here we have a pulley of mass M. So in this case, T1 is not equal to T2. If the pulley is massless, we can say T1 equals to T2. Okay, next. You know, here, any point on the pulley here has a circular trajectory. Okay? The velocity of this point must be tangent to the trajectory. Here we have V. Here also, at any point, must be tangent. If we have a angular speed omega, for example, anticlockwise, and here we have a point A, all have the same velocity. Here we have A, let's say here we have B. We can say VA equals to VB equals to R times omega. And any point on the rim of the pulley, all the points have the same velocity on the rim of the pulley, which is equal to R times omega. Okay? And you know, here the cord is passing through the point A and the point B. So the cord and M2 and the cord and M1 have the same velocity of A and B. So we can say here equals to v1 equals to v2. All these objects have the same velocity v. 5. You know, here, any point here, if we have a anticlockwise rotation omega, so we have a angular speed alpha, any point here has a tangent for this point and for this point. Here, for the point A, we have a tangent of the point A. Here, for the point B, we have a tangent of the point B. You know the relation between a tangent and alpha. We have a tangent of the point A equals to r times alpha. The tangential acceleration of A with respect to the angular acceleration of the pulley. You know also the chord is passing through the point A and the point B. So the acceleration of m2 equals to a tangent equals to a2. So we can say here a tangent of A equals to r omega equals to a1 equals to a, we can say equals to a. Okay, that's all about v of all the system equals to r omega, and a of all the system equals to r alpha. This is in the general case. Now we come back to the problem. We have to find a by using the concept L and alpha. Let me calculate in details the magnitude of L, the magnitude of alpha, and the direction of L and the direction of, no, excuse me, of tau. L and tau. I will find the magnitude and the directions of L and tau in details. Let's say here to calculate L. You know, in general, L equals to R cross P, which is equal to R cross M times V. In general case, first of all, we have to precise 2 points. The system, you know, here we take a system of M1, M2, and the pulley. In this case, L of the system at a time t equals to L1 plus L2 plus L of the pulley. Okay. The second point, we have to precise the calculation of L with respect to which point. We have to say in terms of the point O. O is at the center of the pulley, is here. Okay. First of all, to calculate L, we have to precise the positive direction. We take always the anti-clockwise direction is a positive direction. Okay? So here in this case, we can take to the left and down is positive. And this one is a positive direction anticlockwise. Okay, in general, I tell you how can you calculate the direction directly without using the right hand rule. Okay, you know L depends to the V. If V has a positive direction, like let's say here we have M2, here V has a positive direction. In this case, we can say directly L must be out of the page. Okay, it's outward. And we say in the direction of J. Okay, if V has a negative direction, we can say L must be inward the page in the minus J direction. Okay, you have to know these two notations. We come back to find L, L1 and L2. You know here, let's say L1. L1 equals to R1 cross M V1, MV. First of all, R1 is the projection from the center O to the velocity V1. You know here the velocity of the center of mass must be here. Okay? In this direction. This is the velocity of the center of mass. We do the prolongation of V like this, and the projection from O to the velocity, we get R. This is R1. The magnitude of this one equals to capital R. Okay? So we can write directly here, we have a capital R times M times V times sine the angle between R1 and V. The angle between R1 and V equals to 90. Okay? Equals to 90. You know, first of all, you take R1 is in this direction. You have V is down. The angle between will be from R to V equals to 90. Okay, what about the direction? You know V of M1 has a positive direction. So we can write directly plus J. And you can say L must be out of the page, outward. Okay? So we can write directly here L1 equals to R M V J. What about L2? We can follow the same procedure. Here we have L2 equals to R2 cross MV. R2 as before, here we have the center of mass of M2. Here we have the velocity of M2. The prolongation of the velocity will be like this. R2 is the projection from the center to the velocity. So this is one is R2. The magnitude equals to capital R. So we can write directly here equals to R times M2V times sine the angle between R2 and V equals to 90. As you see, here we have R2 is up, V is to the left. The angle is between R2 and V equals to 90. What is the direction? The velocity of M2 has a positive direction. So we can say directly J. And we can say L2 is out of the page. So L2 equals to R. Here we have M1. Here we have M2 Vj. What about L of the pulley? You know the pulley has a pure rotation. We can say directly L of the pulley equals to I of the pulley times omega. Okay? Times omega. We can write directly in the case of a pure rotation. Okay. You know, here we have only the mass as the rim of the pulley. So it's like a ring. Anyway, you know here I equals to ICM plus MD square. You know ICM, here I give you the value. And D is the distance between the center of mass of the pulley and the axis, which is equal to 0. So I equals to ICM. Here the pulley is, it's like a ring times omega. Here I give you ICM of the ring. As you know, here we have a pulley has only a mass on the rim of the pulley. So ICM of a ring equals to M times R square is a given value. So we can write here I equals to M R square times omega. So we can write here L of the pulley has a magnitude of mr square times omega, and the direction must be, as you know here, omega. In the case of a anti-clockwise rotation, we are in plus j. Okay, plus j, I mean it's outward the page. Because we have a anti-clockwise rotation of the pulley. In this case, L must be out of the page, out in the positive plus J, and plus J. Here I calculated L. We can put L total of the system equals to L1 plus L2 plus LP. We can say equals to R M1 V plus R M2 V plus M of the pulley times R square times omega, all in the J direction out of the page. Okay, you know here we have a relation between V and omega. We calculated before V equals to R times omega. So we can write here in place of omega, we can put V divided by R. We can write V divided by R. So L equals to R M1 V plus R M2 V plus M R V J. This is the value of L. Total L. We can write also here, we can take R, V, a common factor, we get M1 plus M2 plus M J. Okay. What about tau? That's all about L. What about tau? Look here. You know we have a simple relation between tau and L. Summation of tau external equals to dl divided by dt. You know external, I mean all the external forces in the system. We have M1, we have the pulley, we have M2. Here, as you see, the internal is the forces between the objects. For example, here we have T1 and T1. Okay, I don't take about T1. We have T2 and T2 between the pulley and M2. So we don't talk about T2. What is the external? The external is, for example, we have M1G is external. We have R is external. We have MG is external. We have N is external. And we have M2G is external. Okay? So we can talk only about this. First of all, we have R and MG pass through the axis O. We can say tau of mg equals to tau of r equals to 0. Why? Because pass, we can say because they are through the axis. What about M1G and M2G and N? You know, M2G and N, they don't have any effect to the rotation. Okay, they will not contribute to the rotation. M2 will not turn the pulley, and N also will not turn the pulley. So they don't have effect to the rotation. In this case, we can say tau of n equals to tau of m2g equal to 0, because we can say here n and m2g don't or we can say do not contribute to the torque. What I mean, m2g is pushing down m2, it doesn't have any contribution to the torque. It doesn't have the ability to turn the pulley. N is pushing up like this. N doesn't have any contribution and it doesn't have any ability to turn the pulley. In this case, we can say N and M2G do not have any contribution to the torque. Okay, so in this case, we have finally summation of the external tau is only of M1G, because if M1G push down the cord, in this case we get a rotation. So here we have tau of M1G, which is equal to dl divided by dt. Here, what about the positive and the negative? What about the direction of tau? You know, here we have the positive direction is down, anti-clockwise, and here to the left. This is the positive direction. The value of tau equals to R cross F, okay, which is equal to dl divided by dt. Like before, like in the case of angular momentum, R is the projection from the center to the prolongation of mg. Here we have m1g, m1g. We do the prolongation. We answer the projection from the center to mg. We get here R. The magnitude equals to capital R. So we can say here R times M1G. What is the direction of this one? You know, mg is in the positive direction, so we can say directly J. And we can say it's out of the page. When we have anti-clockwise, in the case of anti-clockwise motion, we have L must be out of the page and tau must be out of the page. In the case of clockwise, L will be into the page and tau will be into the page. And here we have plus J, minus J. Here we have minus J. Okay, so here finally we can write the summation of external equals to R M1G, J equals to D divided by dt of L, which is equal to M1 plus M2 plus capital M R V like this, J. Okay. You know here M is constant, M2 is constant, M is constant, R is constant. We have only V is not constant. So we can write R M1 G J. Here we can cancel J. We have J and J. So equals to M1 plus M2 plus capital M R dV divided by dt. You know that A equals to dV divided by dt. This is the value of A. So A is equal to, we can eliminate R and R, we get finally M1 plus M2 plus M divided by, no. We have M1 divided by M1 plus M2 plus M. This is the value of A. You have to know, you have to understand all the points. How can we calculate the angular, the acceleration of M1 and M2 by using L and tau concepts? It's very important. You have to follow the same procedure. The most important point here, first of all, you have to know that L must be defined by V, tau must be defined by F. What I mean? Here we have a positive anticlockwise direction. If V has a positive direction, we can say L has a J direction, must be out of the page. If F has a positive direction, we can say tau has a J direction out of the page. Okay? In the case of a negative direction of V and F, okay, if V has a negative direction, so L must be in the negative J. It must be into the page. If F has a negative direction, we can say tau equal to the magnitude times minus J. And it must be inward the page. This is the first important point. The second point, the summation of tau external equals to dl divided by dt. This is only the external, only the external. Any internal f between the objects, we don't talk about. External, we have, for example, mg. Here we have mg, we have n, we have r. Okay? Thank you.